Hello friends, in the previous lecture we discussed the solution of radiative heat transfer in one dimensional media. In this lecture we will study approximate methods for the solution of radiative transfer equation. Now when we talk about approximate methods, there are number of ways we can approximate the radiative transfer equation. Some of these approximations are based on the properties of the media, such as the absorption coefficient and scattering. We can assume non-scattering media, we can assume non-absorbing media, we can assume isotropic media, we can have the choice to assume that the medium is optically thin, that is kappa lambda is very small. We can have the choice to assume that the medium is optically thick or cold. So these are basically the approximation based on the properties of the medium, the absorbing scattering medium. The second way to approximate the radiative transfer equation is by approximating the geometry of the problem. As we discussed in the previous lecture, we can have one dimensional problems, plane parallel slab or cylindrical media, where the radiative intensity is a function of one space coordinate. In plane parallel slab, the intensity was just a function of z and theta, while for the cylindrical media it was function of r, theta and psi, the polar and azimuthal angle. The third level of approximation is based on the intensity itself, and this is the approximation which is mostly used in many commercial radiative transfer solvers. The reason is the approximation on radiative properties, assuming them to be optically thin or thick, is very restrictive. We have very less practical problems where we have optically thin or thick media. So this approximation is theoretically good, but has very limited practical value. Similarly, one dimensional problems like cylindrical problems or plane parallel slab also have very limited applications. On the other hand, most of the practical problems are 2 dimensional or 3 dimensional with continuously varying properties, and therefore the two approximations that I just mentioned are not valid. So the third approximation based on the direction of the intensity is used in many radiative solvers to solve the radiative transfer equation. So I will just quickly explain you the effect of this intensity. So in practical problems, at any point the intensity may vary in a certain manner. So this is, let us say, point P, and the intensity may continuously vary along the solid angle. It may be very large at certain angle, and then it may continuously vary. So the intensity is a function of theta and mu. Okay. So we see that there is a continuous variation of intensity with respect to direction. Now many methods basically approximate this dependence. For example, the two flux approximation assumes that the intensity can be assumed to have this type of variation, where we have intensity one value for the downward direction and another value in the upward direction. That is, for mu 0 to 1 we have one value of intensity, and for mu minus 1 to 0 we have another value. So this is basically two flux approximation where we have approximated the intensity to have two values. Similarly, we can always assume the intensity to be isotropic, that it is same in all direction. So this is the approximation which is used in many methods which we will discuss, but in this lecture we will focus our attention on the approximate methods where we are approximating the properties of the medium, the absorbing scattering medium, and the first in this category is optically thin approximation. So optically thin approximation is a case where the absorption coefficient is small, the optical path length is very small. So, we assume now in this case there is a medium bounded between two parallel plates. These plates are gray and they are diffusely emitting and reflecting surfaces. The temperature of the plate is uniform, so they are isothermal. So, we have already derived a solution for this problem in the previous lecture. So, the expression for incident radiation G tau. So, we know that the radiation is the incident radiation and heat flux is going to vary with the coordinate tau. So, tau is equal to 0 at the bottom plate, this is plate 1, this is plate 2. So, tau is 0 at the bottom plate and tau is equal to tau L at the top plate. So, the incident radiation varies with tau and the expression is 2 times J1 exponential integral of second order plus 2 times J2 then exponential integral of second order tau L minus tau, and then the 2 integrations on the right hand side each having the source term as an integrand. So, this was the solution we derived in the previous class, and similarly for radiative heat flux we have this expression q tau is equal to 2 J1. Now, we have exponential integral of order 3 minus 2 J2 E3 tau L minus tau, and then the 2 terms for the source term. So, this was the expression we derived in the previous class for heat flux and incident radiation as a function of tau between two parallel plates. Now, let us see if we can simplify this solution. So, this solution we have, the only problem in this solution is that we have to evaluate the integrations and exponential integrals as appearing in these two equations. So, we assume that tau L is very less than 1, that is the medium is optically thin. So, when the medium is optically thin, all we need to do is we have to evaluate the exponential integrals for order 1. So, this is the term of order x and above which are neglected. So, we write exponential integral in terms of a series, and the first term is only retained, rest of the terms order x and higher are basically ignored. Similarly, in exponential 3 integrals the term half n minus x is retained, that is all the terms of order x square and higher are basically ignored. When we do such an approximation, the heat flux evaluated will be accurate up to order tau. So, we want that heat flux should be accurate up to order tau, and that is why we have approximated the exponential integrals, and when we do that we substitute the value of E2 tau and E2 tau L minus tau in this expression for G tau and exponential 3 integrals in q tau. So, our heat flux is basically simplified to J1 1 minus 2 tau and J2 1 minus tau L plus 2 tau. Okay. So, the first two terms in the expression of heat flux have been simplified, we do not need to evaluate the exponential integrals, and the solution is relatively simple. Now, let us see what we can do for the next two terms, that is integration over the source term for an optical thickness 0 to tau and tau to tau L. So, let us see. Now, for this we write the radiative source term first. So, radiative source term basically has a contribution from emission and contribution from scattering. So, these two terms we have to approximate if we want to approximate G tau for order 1 and higher. So, one thing you should note that if these two terms are order tau, the order of accuracy of the first two term is order tau, then the integration need to be evaluated for order 1 only, okay, because when we integrate an order of accuracy is increased. So, we need to evaluate the incident radiation G tau for order 1, okay, and we do that from this expression for G tau. So, in this expression we approximate this expression for order 1. So, the integrations, these two integrations are ignored because their accuracy is less. So, we ignore the last two terms in the expression of G tau, and our G tau is simply written as 2 J1 plus to J2 and rest of the terms are ignored. Okay. So, this G tau is accurate to order 1. Okay. So, this expression of G tau is substituted in this equation, and when we do that we receive the value of the source term as 1 minus omega I b plus omega upon 4 pi, and then this will be simply 2 J1 plus J2. So, now this expression we have simplified significantly. Now, this value of the source term S tau we will put in the expression of heat flux here. So, the expression for heat flux contains two integrations, and the integrand is a source term, and this source term we have simplified as 1 minus omega I b plus omega upon 4 pi to J1 plus J2. So, when we substitute this the expression basically is simplified significantly, and this is the expression for the radiative heat flux, and the only quantity now appearing in the integration is just black body emissive power emissive intensity, that is I b. Okay. So, this is the approximate result for the heat flux in under optically thin approximation. Now, the expression for divergence of heat flux del dot q is equal to, as we already know, this is given by 2 1 minus omega 2 pi I b, and then we have to put the value of g here. So, this will be g by 2. So, substituting for g from this equation, this expression for del dot q is basically found. Okay. So, this is the expression for heat flux and del dot q under the assumption that we have optical thickness very less than 1, that is the optically thin approximation. Now, if we have radiative equilibrium, then the analysis is pretty simple. For radiative equilibrium we have del dot q is equal to 0. So, we put the expression of dq by d tau as 0, and we get J1 from this expression. Basically we get g is equal to 2 pi. So, from this we get g is equal to 4 pi I b. Okay. So, that means the source term is equal to simply the black body intensity, and this can be written in terms of wall radiosities J1 and J2. Okay. So, this is very much simple, very simplified for optically thin approximation. Similarly, the radiative heat flux under radiative equilibrium is simply a function of J1 and J2, and the expression q is equal to J1 minus J2 multiplied by 1 minus tau L, and this is basically constant. So, that means the radiative heat flux is not a function of, it is not a function of tau anymore. Okay. So, this is constant, and here also radiative source term is not a function of tau, that is it is constant. Okay. So, what we have done here is we have found the expressions for radiative heat flux and radiative heat source term for optically thin cases where the absorption coefficient is very small, and we have derived simplified expression. The other end of this analysis is optically thick approximation. In optically thick approximation, the absorption coefficient is going to be very large. So, for optically thick cases, the tau L is going to be large, and the value of absorption coefficient is large. So, tau L is going to be very greater than 1. Now, what we observe here, that for optically thick cases the exponential integral will decay very fast. That means, for the point under consideration, if you move little bit farther from that point of interest, then the exponential integral will decay very fast. So, let us say we are interested in finding the expression for heat flux or intensity at this point P, then only certain small distance away from P the source term will become negligible. That means, the effect of intensity coming from this point will be negligible, and based on the same argument, the radiative intensity coming from plate 2 and plate 1 will not reach P, it will be absorbed within the small distance. Okay. So, it will be absorbed here and it will be absorbed here. So, radiation starting from plates 1 and 2 will not reach point P, it will be absorbed within small distance away from the plates, and the reason is the absorption coefficient is large, the attenuation is very large, and the radiation is basically not reaching point P. The radiation from plates is not reaching point P. So, what we have is basically only the local effect. So, point P finds itself in a position where the intensity at point P is affected by only the local phenomena, and long distance effects are basically negligible because of the significant amount of attenuation taking place. So, under this assumption we can express our source term with a Taylor series, where we are saying that at point P the source term is affected by intensity within small optical distance plus minus tau double prime, that is point P is affected by radiation within a small circle of optical thickness represented by tau double prime. So, we express this with the help of Taylor series. So, we write S tau plus tau double prime as S tau and then the first derivative and the second derivative terms. So, this is the Taylor series approximation of the radiative source term. When we substitute this in the expression of heat flux, so we have the expression of heat flux, the first two quantities are automatically 0 because the effect of wall radiation is not observed, as I already explained. J1 and J2 will not appear in the expression of heat flux because the effect is all local, the long distance effect is not felt in the heat flux. So, for any point within the medium the wall radiation will not take place, and the second two terms, the last two terms will basically appear, and these two terms also we have approximated using the Taylor series. When we do that, the expression of radiative heat flux Q tau contains only this integration and derivative of the source term ds by d tau. So, we have neglected the second order and higher terms, and our expression for heat flux becomes simply minus 2 ds by d tau and then integration from 0 to infinity x e to x dx. Okay. So, so with this this expression is basically for optically thick case. Okay. Now, evaluation of the integration in this equation is relatively straightforward. So, this integration basically evaluates to 1 by 3, and with this we get the radiative heat flux as equal to minus 4 pi by 3 ds by d tau. So, for optically thick cases the expression of heat flux is very simple, and it is given by q tau is equal to minus 4 pi by 3 ds by d tau, where S is now the source term at any location tau. Now, if the medium is not scattering, then S is simply equal to IB, and we can just write down our heat flux equation substituting S is equal to IB. So, q tau is equal to minus 4 pi by 3 dIB by d tau, and if we write in terms of absorption coefficient, then we have d tau is equal to kappa times dz. So, this is tau. So, d tau is equal to kappa times dz. The expression for radiative heat flux at any location within the medium is minus 4 pi by 3 k kappa dIB by dz. For an isotropically scattering medium, same thing. If we do not have purely absorbing media, we have scattering also. The expression remains the same, only thing is kappa is replaced by beta, where beta is now the absorption coefficient kappa plus scattering coefficient sigma. So, beta is the extinction coefficient, rest of the expression remains the same. The same thing is valid for spectral basis also. This is where we have not used the wavelength, but we can write the same expression for wavelength also. So, q lambda is equal to minus 4 pi by 3 beta lambda d IB lambda by dz. So, the expression is valid for spectral basis also, and we have replaced the kappa or beta with the spectral absorption or extinction coefficient beta lambda, and the black body intensity is replaced by spectral black body intensity IB lambda. The expression remains the same on spectral basis also. Now, we can integrate this to find out the total value of heat flux. So, this expression was for gray, this is for non gray, that is on a spectral basis, and this is for total. So, total means we have to integrate over all the wavelengths. So, q will be simply equal to q lambda d lambda 0 to infinity. So, this will be the total heat flux. So, when we integrate this expression, the expression for heat flux q on total basis is simply equal to 4 sigma. Now, pi times I b lambda we write as equal to E b lambda, that is the black body emissive power, and when we integrate over all the wavelengths we get sigma T power 4. So, the expression becomes q is equal to minus 4 sigma by 3 beta r d T power 4 dz. Now, beta r is basically Rosland mean absorption coefficient. So, beta r is defined as Rosland mean extinction coefficient. We define this extinction coefficient as basically the mean value integrated over all the wavelengths. So, 1 upon beta r, where beta r is the Rosland mean extinction coefficient, is equal to 1 upon sigma T power 4, then integrating from 0 to infinity on all wavelengths pi times I b lambda over beta lambda, that is pi times I b lambda is nothing but E b lambda. Okay. So, this is how we calculate this mean extinction coefficient. So, 1 upon beta r is basically given by this relation, and this relation is basically called Rosland mean extinction coefficient, and this method for optically thick cases is called Rosland approximation or diffusion approximation. Now, why it is called Rosland diffusion approximation is because the radiation effect is local, that is the intensity at a given point, P is affected by only a small region around P. What is happening at the wall is not affecting P. So, how much energy is coming from the wall is not basically affecting P. So, radiation at P is affected by locally, and this is very similar to what we have in conduction, where heat transfer basically takes place due to phonon-phonon interaction at a local level. So, that is why it is the method is also basically called diffusion approximation. And we can also define, because the method under optically thick cases is very similar to conduction cases, we also define a quantity called radiative conductivity, and this can be calculated based on the expression of radiative heat flux. So, q is equal to minus 4 by 3 sigma beta r sigma upon beta r d T power 4 by dz. Now, this can be written as minus 4 by 3 sigma upon beta r, and this will be equal to 4 times T cube dz dt by dz. So, we can write this as minus k. Now, this k is not kappa, this is absorption coefficient, or rather called radiative conductivity k r, k subscript r dt by dz. So, this is very similar to the expression of conduction, thermal conduction. We can define a radiative conductivity for optically thick cases, because the radiative heat transfer in optically thick cases is very similar to the conduction, and this k r is nothing but 16 sigma T cube upon 3 beta r. N just represents the refractive index, which is normally equal to 1. So, the expression is simply sigma T cube by 3 beta r times 16. So, this is the radiative conductivity. So, we learned in this chapter two methods, the optically thin approximation and optically thick approximation. We will solve one problem, and in this problem we will see how to find out the temperature and heat flux inside a non-scattering medium bounded by two isothermal black cylinders. So, let us say we have two cylinders. This is the outer cylinder, and we have an inner cylinder. Okay. So, we have both the cylinders are black, that means the emittance is equal to 1. Okay. The inner cylinder has radius r1 and temperature is T1, outer cylinder has radius r2 and temperature is T2. Okay. So, we have to find out temperature and heat flux inside a gray non-scattering medium. So, this is non-scattering medium, sigma is equal to 0, the surfaces are black, and we assume radiative equilibrium, that means dq by d tau or del dot q is equal to 0. Okay. So, we will use a cylindrical coordinate system. In cylindrical coordinate system, we have del dot as written by 1 by r d by dr r times q. So, this is the expression for del dot q in cylindrical coordinates, and this will be equal to 0 because of radiative equilibrium, this will be equal to 0. So, this means r times q is constant, let us call this constant C1. So, RQ is constant, or radiative heat flux varies inversely with respect to R. So, Q is equal to C1 by R, radiative heat flux varies inversely with respect to R. Okay. Now, from the previous result for optically thick cases, we have the expression for radiative heat flux was Q is equal to minus 4 sigma 3, this was the expression, minus 4 pi by 3 dIb by d tau. So, we can write this as, this will be equal to minus 4, if we are talking about total basis. So, minus 4 sigma by 3 d T4 by d tau. Okay. So, this was the expression for the heat flux under optically thick cases, that is the diffusion approximation. Now, we will write this as C1 by R as equal to minus 4 sigma by 3 d T4 by d tau. So, now let us solve with this. So, we write this as sigma T power 4 as equal to minus 3 by 4 C, this was expression for C1. So, C1 ln tau plus C2. Okay. So, what we have done is we have integrated with respect to tau, and we got this result sigma T power 4 minus 3 by 4 C1 ln tau plus C2. So, this gives an idea of how the emissive power within the medium is changing with respect to the coordinate tau. Now, boundary condition, although the expression for optically thick cases that we derived was valid for any point away from the surface. So, remember we derived the optically thick case for a point P away from the plates. Okay. If it is at the plate, then the expression is not valid, but we are trying to apply this to this cylindrical configuration, assuming that the cylinder can be opened up in the form of parallel plates. So, we have approximated the cylinder in the form of parallel plates, and we are applying the boundary conditions at the wall. So, with boundary conditions we say T is equal to T1 at R is equal to R1 and T is equal to T2 at R is equal to R2, and with this substitution in the equation, let us call this equation 1, we put this boundary condition to find unknown coefficient C1 and C2. Okay. And when we find C1 and C2, we get this expression for the temperature T power 4 minus T1 power 4, T2 power 4 minus T1 power 4. This is basically the non-dimensional MSC power. So, tau by tau 1 upon ln tau 2 by tau 1, where tau 1 is nothing but the Gray absorption coefficient kappa times R1 and tau 2 is Gray absorption coefficient kappa times R2. So, we get this distribution for the MSC power, non-dimensional MSC power or temperature power 4, and similarly the radiative heat flux Q is equal to sigma T1 power 4 minus T2 power 4 is equal to 4 by 3 tau ln tau 2 by tau 1. Okay. So, this is the expression for the non-dimensional radiative heat flux. We have found this expression using C1 by R. So, we have calculated the unknown coefficient C1 already. So, the expression for the non-dimensional radiative heat flux Q upon sigma T1 power 4 minus T2 power 4 is simply equal to 4 by 3 tau ln tau 2 by tau 1. So, these two solutions we have found for the case of cylindrical media approximated using the diffusion approximation, that is optically thick approximation. Now, these results are plotted on a chart, and as you see that this is the results for the diffusion approximation, the Rosalind approximation. For small values of tau, that is small tau, optically thick case is not valid, and definitely the results obtained with this methods are not accurate. Why? Because this method is derived for optically thick cases, that is tau values large. For tau values small, the optically thick approximation is less accurate, and as is seen, the square represents the exact solution and this represents the Rosalind or diffusion approximation, and the results are very much inaccurate. On the other hand, we see that the results are relatively good for optically thick cases, that is the value of optical thickness is large and the results are relatively more accurate and they match relatively better with the exact results. Although there is still some problem at the wall, there is a jump at the wall, and the reason for this jump is that we have applied this method diffusion approximation to at walls. So, we have applied this method at walls, while the method itself was not derived for walls. The method was derived for finding radiative heat flux away from the walls, where the effect of walls was negligible, while in this problem we have applied this method to find out radiative heat flux very much near the wall, and that is why there is a jump here, and this jump needs to be taken care. Otherwise, this method is good only for points away from the walls for optically thick case. So, thank you. In the next lecture we will introduce other methods, other approximate methods, and these methods will be based on approximating the intensity variation as opposed to the approximation of properties optically thin or optically thick assumed in this lecture. Thank you.